Welcome to Talk Treatises.
It's great to be here.
Today we're doing something I think is probably more fundamental than talking about the latest headlines or, some new gadget. We're going back.
Way back.
We are going back to the source code, to the operating system of how we think. We are opening a very dusty, very important book from the late 19th century to try and understand a mind that wanted to turn the whole messy, chaotic business of human reasoning into a perfect, frictionless machine.
And a silicon machine. A machine made of wood and brass, no less.
Exactly. We are diving deep into a truly seminal and I think criminally overlooked masterpiece of logic and scientific philosophy. It's called The Principles of Science, a treatise on logic and scientific method.
And it's by William Stanley Jevons. I have to agree, masterpiece is the right word, but it is a formidable one. It's dense. It was published in 1874, which is a really, really specific moment in time.
Okay, let's set the scene then. For you, the listener, picture it. 1874, Queen Victoria is on the throne in Britain. What does the world look like to a scientist? What's in the air?
Oh, it's a time of absolute explosion. Just an explosion of discovery. The physical sciences are just leaping forward at a pace that's almost hard for us to comprehend now. Yeah. Because we're so used to rapid change.
Right. For us, it's normal.
But for them, it was brand new. You had thermodynamics finally being codified. You have electricity going from, a parlor trick with static to a genuine world-changing infrastructure. Chemists are busy filling in the periodic table. There was this feeling, this optimism that humanity was finally truly mastering the physical universe.
The whole clockwork universe idea was really at its peak, wasn't it?
Precisely. The idea that if we just measure enough things, precisely enough, we'll eventually know everything. But Jevons, he saw a gap. A really dangerous gap, actually. He looked at his colleagues, the brilliant physicists, the chemists, the astronomers, and he realized something.
What was that?
While they were all busy doing science, if you stopped one of them and asked, okay, can you please define the scientific method with absolute logical rigor? They'd probably stumble.
So they were flying the plane, but they couldn't actually explain the principles of aerodynamics.
Or maybe the aerodynamics of thought itself.
Yeah.
They were operating on intuition, on tradition, on habit. Jevons decided to step in and fix that. He wanted to map out the software that was running in the background of every scientist's brain. And, he wasn't just some philosopher in an armchair.
No, he was a true polymath.
He was a logician, a pioneering economist. His work on marginal utility is foundational. He was a meteorologist, a scientist himself. He was in the trenches.
And when you read the text, you just get this sense of an intellect that is, it's just frighteningly sharp.
Oh, absolutely. I mean, you have to imagine an IQ that you'd statistically place, 3 standard deviations above the norm? He didn't just want to describe science. He wanted to unify it. He wanted to show that the laws of human thought were just as rigorous, just as determined as the laws governing the orbits of the planets.
And what he builds is this massive intellectual framework. It starts with literally the simplest possible idea you can imagine, and by the end, he's talking about the heat death of the universe and the nature of God. It's an incredible journey.
It really is.
So let's start where he starts. The hook, the central premise. Jevons makes this audacious claim that all reasoning, everything, whether you're a detective solving a crime, an astronomer calculating an orbit, or just, deciding if a coin is counterfeit, all of it reduces down to a single fundamental principle.
The principle of the substitution of similars.
I have to be honest, when I first read that phrase, the substitution of similars, it sounded a little dry, a bit academic. It sounded like a grammatical rule you forget the moment you leave middle school.
It definitely lacks a certain marketing flair, doesn't it? But for Jevons, this is it. This is the atom of thought. If you could split the atom of reasoning, this principle is what you would find inside. The one-sentence thesis of this whole massive work is that science is just the rigorous application of formal logic and probability. And all of it, every last bit, rests on our ability to substitute one thing for its like.
Okay, so let's unpack that. The substitution of similars. What is the core axiom? What's he actually saying?
The axiom, as he defines it, is this. Whatever is true of a thing is true of its like or equivalent.
That sounds tautological. It sounds like A equals A. If I have this red apple and I swap it for an identical red apple, I still have a red apple. Is that really the foundation of all science? Is that the grand secret he uncovered?
It seems trivial on the surface, doesn't it? Yeah. But Jevons argues that this is the absolute mechanism of all inference. The power isn't in the statement A equals A. It's in how we use it as a tool to move from something we know to something we don't. Think about how you actually prove something in the real world. You almost never compare two things directly in a vacuum. You almost always need a bridge, a go-between.
A bridge.
A mediator, a third term. Jevons uses this classic perfect example of tuning forks.
Right, I remember reading this. Walk us through the tuning forks, because I think it makes it really clear.
Okay, so suppose you have two tuning forks. Let's call them fork A and fork B. You want to know, with scientific certainty, if they have the exact same pitch. So you struck them both.
Mm-hmm.
Now, unless you happen to have absolute perfect pitch, which, most of us don't, you can't be 100% sure just by listening to them one after the other.
Right. My brain might tell me they sound close, but I can't be scientifically certain they're identical. There could be a tiny difference I'm not hearing.
Exactly. So direct comparison fails us. What do? You bring in a third standard sound, let's call it sound C. Maybe it's a very precise electronic tone generator. You strike fork A and you compare it to sound C. If they are in perfect unison, no beats, no dissonance, you've established an identity, A equals C.
Okay, so I've now anchored fork A to a known standard. I have a fact.
You have a fact. Then you put fork A down, you pick up fork B, and you compare it to the very same standard, sound C. If fork B is also in perfect unison with C, then you have a second identity, B equals C.
And because A equals C and B also equals C.
You can perform the substitution. In the equation B equals C, you can substitute the C with its known equivalent A. Therefore, A equals B. You have just proven that the two forks are identical without ever directly comparing them to each other.
You use the go-between.
You use the substitution of similars to transfer the property of being equal to C from one object to the other. And that is inference.
So the complexity isn't in the rule itself, it's in finding that third term, that standard to compare everything against.
Precisely. And Jevons just scales this concept up to everything. He says, this applies to specific gravity. If I hand you a lump of mystery metal and you run a test and find it has the same specific gravity as gold, which is our standard C, and then you find it has the same melting point as gold and the same chemical reactivity as gold.
Then at some point, I can just substitute the words mystery metal with the word gold.
And the moment you make that substitution, you unlock a universe of other knowledge. Suddenly you know it will conduct electricity in a certain way, you know it won't rust, you assume all the properties that belong to the class gold now apply to this specific lump of metal in your hand. That's the leap. That's inference.
It's really the logic of pattern recognition, isn't it? This thing acts like X, therefore it is an X, therefore it will continue to act like an X.
It's what he calls the great rule of inference. And he argues there's no other kind of reasoning. But he doesn't just stop there at the concept. He tries to build a formal language out of it. And this brings us to what he called the logical alphabet.
This part of the book really blew my mind. I mean, he basically invents binary code a full century before the electronic computer.
He really does. He first calls it the logical abecedarium, which is a bit of a mouthful.
A little pretentious, maybe?
Yes. He later simplified it to logical alphabet because he admitted people complained about the name. But the concept underneath is incredibly modern.
So he says, if you have a set of terms, let's use his example, A, B, and C, you can't just think about them casually. To be rigorous, you have to exhaustively list every single possible combination of their presence and their absence.
Exactly. The whole system rests on what logicians call the law of duality, or the law of the excluded middle. A thing must either be or not be. There is no third option. There's no kinda. You are either made of iron or you are not iron. You're either magnetic or not magnetic. It's a binary state.
So let's make that concrete. If we have just two terms, A and B, what does that list of possibilities look like?
You'd have four possibilities in your universe. You have AB, which means the presence of both properties. You have AB, which is the presence of A and the absence of B. You have AB, the absence of A and the presence of B. And finally, you have AB, the absence of both.
And he very cleverly uses lowercase letters to represent the not state, the zero state.
Precisely. It's binary. It's 1 and 0. And it scales. If you have 3 terms, you have 2 to the power of 3, so 8 combinations. 4 terms, you get 16. It grows exponentially.
Okay, but what's the point of this? Why write out this enormous list of every possible world?
Because, Jevons says, the entire job of science and reasoning is to cross things off that list. Reasoning, for him, is fundamentally a process of elimination.
It's like the game Guess Who.
That is a perfect analogy.
Yeah.
Absolutely perfect. And guess who? You start with all the faces visible. That's your logical alphabet. It's the universe of all possibilities. Then what do? You ask a question. Does your person have glasses?
And if the answer is no, I immediately flip down all the faces that are wearing glasses.
You eliminate the contradictory combinations. Jevons says that is exactly what we do in logic. If we are given the premise, the scientific law, that all iron is magnetic, we look at our logical alphabet of possibilities. We find the combination that represents iron and not magnetic.
We flip it down. We cross it out.
We strike it out. It's a world that cannot exist under the law we just stated. And you just keep doing this. You add more premises, more laws, and you keep crossing out the impossible worlds until the only things left standing on the board are the necessary truths.
And he didn't just write this down as a theory. This is the amazing part. He built a machine to do it. The logical piano.
This is one of the most fascinating artifacts in the entire history of computing, I think. He actually constructed a physical machine with keys, like a small upright piano.
Describe it for us. What did it look like?
Okay, so imagine a wooden box, maybe about 3 feet high, with lots of intricate brass fittings. On the front, it has a face, a set of windows that display the logical alphabet. All those combinations of letters we were just talking about, like A, B, AB, A, B, A. And below that, a keyboard.
And you would play the premises on the keyboard.
You'd hit keys that represent logical statements. There'd be a key for all A is B or no B is C. And inside this box was this incredibly complex system of levers, rods, and pulleys. When you press the keys, it would mechanically cause little wooden slats to lift up and cover the contradictory combinations on the display.
So if you typed in the premise iron is a metal, the machine would physically hide the possibility of iron is not metal from view.
Yes. It mechanized the substitution of similars. It was a physical demonstration that logical inference isn't some magical, mysterious process of the soul. It's a mechanical process. And Jevons knew exactly what he was doing. He wrote that his machine proved that the mind's most abstract logical operations could be performed by brass and wood.
It's the great-grandfather of the modern computer.
It is. At its core, your smartphone is just an incredibly fast, logical piano, processing billions of binary states through logic gates.
It's just incredible to think of this Victorian gentleman in a waistcoat and tails building a wooden computer to mechanize thought. But okay, let's bring this back to how it applies to the real world, because we can sit around pushing keys on a logical piano all day, but science is about discovering new things. And this brings us to what you called the great reversal in segment 2.
Yes, the relationship between deduction and induction. And this is a real philosophical battlefield.
Right. So traditionally, deduction is top-down. You go from the general to the specific. The classic example. All men are mortal, Socrates is a man, therefore Socrates is mortal. It's certain.
And induction is the opposite, bottom up. You go from the specific to the general. This swan is white, and that swan is white, and every swan I've ever seen is white, therefore all swans are white.
And that's not certain.
Not certain at all. That's the standard view from Aristotle. But then Jevons comes along and makes this incredibly bold, incredibly controversial claim, he says. There is no distinct method of induction.
Wait. What? That sounds like he's trying to destroy the foundation of science. If there's no induction, how do we ever learn general laws from specific observations?
He's not saying it doesn't happen. He's saying it's not its own thing.
Yeah.
He argues that induction is simply inverse deduction.
Inverse deduction. Okay, what does that mean?
Think of it like a cipher or a code. Deduction is like encoding a message. It's straightforward. Induction is decoding it. It's working backward from the scrambled message to find the original key.
He uses this beautiful analogy from mathematics to explain this, with multiplication and factoring.
Yes, and let's walk through that because it perfectly illustrates the central difficulty of doing science. Multiplication, he says, is deduction. If I give you 2 prime numbers, say, 17 and 23, and I ask you to multiply them, that's a deductive process.
Right. There's a clear method. A set of rules. I multiply the 7 by the 3, carry the 2. I follow the steps, and I will get the answer 391 with absolute 100% certainty. It's mechanical. Simple calculator can do it.
But now, what if I reverse the problem? What if I just give you the number 391 and I ask you, what 2 numbers were multiplied together to produce this?
That's factoring.
That is factoring. And that, Jevons says, is induction. You are looking at the result, the phenomenon you see in nature, and you are trying to work backward to find the factors, the scientific laws that produced it. And as he points out, that is infinitely harder. There's no simple direct method.
You basically just have to guess and check.
You have to try keys in the lock. You try dividing 391 by 3, nope, by 5, nope. You formulate a hypothesis, maybe one of the factors is 7, and then you deduce the result of that division to see if it works.
So nature presents us with the final number. We see the tides, the orbits of the planets, the apple falling from the tree. Those are the products.
And our job as scientists is to guess the factors. We have to guess at the laws of gravity or fluid dynamics or whatever it is that multiplied together to create that result we see. And because it's this difficult inverse process, we can't just create knowledge out of thin air. We can only try to decipher the hidden contents of our observations.
And this whole line of thinking leads Jevons to a really blistering critique of one of the heroes of science, Francis Bacon.
Oh, poor Francis Bacon.
Yeah.
He's usually hailed as the father of empiricism, right? The guy who told everyone to stop reading ancient Greek philosophy and actually go out and look at the world. But Jevons just goes after him hard.
He really does. He attacks what was known as the Baconian method, which was this popular idea that science is just about collecting massive amounts of data. Bacon seemed to think that if you just wrote down enough facts, he called it ledger keeping, essentially, the truth would just spontaneously emerge from the data.
The ledger fallacy. It's like, if I just go outside and write down the temperature every single day for 1,000 years, the complete laws of thermodynamics will just magically pop out of the page at me.
Jevons says, absolutely not. You can't just pile up random facts. It's useless. Yeah. You need a hypothesis first. You need a question. You need to know what you're looking for. He argues that Bacon, the great philosopher of science, actually misunderstood how the greatest scientists worked in practice.
Bacon was more like the administrator of science, not the actual practitioner on the front line.
So if Bacon got it wrong, who is Jevons' hero? Who got it right?
Isaac Newton, without a doubt. Jevons champions what he calls the Newtonian method.
And what does that look like?
It's a 3-step dance. Step 1, form a hypothesis. Make a guess. It could be a wild, creative guess. In fact, Jevons thinks it should be a wild guess.
Okay, step 2.
Deduction. This is where the logic comes in. You use mathematics, you use logic, you use the substitution of similars to rigorously calculate what must happen if your wild guess is actually true. If my hypothesis about gravity being an inverse square law is correct, then the moon must fall away from a straight line path by exactly this much every second.
A testable prediction. And step 3.
Verification. Go to the experiment. Go look through the telescope. Does the moon actually fall by that predicted amount? If yes, your hypothesis survives. You're onto something. If no, your hypothesis is wrong. Throw it out and make a new guess.
It's interesting because this really emphasizes creativity. Jevons seems to think the ideal scientist needs to be almost romantic, an artist.
He says that explicitly. He argues a scientist must be a creative romantic. You need that soaring imagination to formulate the hypothesis in the first place. The cold, hard logic only comes in later, in the testing phase. He famously calls Newton's Principia the true novum organum, the true new instrument of science, effectively replacing Bacon's work of the same name. You have to imagine a possibility like gravity acting mysteriously across empty space, which is a completely bonkers idea at the time, and then you have to be ruthless in testing it.
But even if we test it and it works every time, Jevons says we're still never actually finished. We're never certain. And this leads us perfectly into segment 3, probability.
Yes. And his chapter title for this is The Measure of Ignorance. This is such a profound shift in how we think about truth. Jevons argues that probability belongs wholly to the mind. It does not exist in nature.
What does that even mean? A coin flip isn't random. That feels deeply wrong.
Not to the coin, no. In this sense, Jevons is a complete determinist. He says nature is determined. When you flip a coin, it's not a random event. It's obeying the laws of mechanics, air resistance, gravity, the initial angular momentum from your thumb. If we could know every single one of those forces, the exact micron-level twitch of your thumb, the humidity of the air, the tiny air currents in the room, we could calculate the result with 100% certainty before it even landed. It doesn't choose to be heads or tails.
So chance is just a word we use because we're stupid, or we don't have enough information.
Exactly, because we are ignorant. We lack the data or we lack the computing power to process it. So for Jevons, probability is simply a mathematical measure of our own lack of knowledge. And to explain this, he uses this incredible metaphor, the infinite ballot box.
I loved this image. The entire universe is a ballot box.
Imagine a gigantic ballot box that contains an infinite number of balls. Some are black, some are white, but we have no idea what the ratio is. All we can do is reach in and pull out a few, and those are our experiences, our scientific observations.
So if I see the sunrise every single morning for my entire life, that's just me pulling out a white ball, then another white ball, then another white ball.
Exactly. And based on that sample, we try to infer the contents of the entire infinite box. But, and this is what he calls the sunrise problem, Just because you've drawn 10,000 white balls in a row does not logically prove that the next one you draw must also be white.
It only makes the probability fractionally higher. It increases my confidence, but it never, ever reaches 100%.
It can never reach certainty. Jevons is incredibly strict about this. He states that we can never be absolutely certain of any future event. The sun rising tomorrow is a hypothesis with a very, very, very high probability, but it is not a logical necessity. There could be a black ball buried deep in that infinite box that we just haven't happened to touch yet.
This is what he calls the rule of succession. We have a formula for calculating the likelihood of the next event repeating the last, but the denominator in that fraction is always growing with each new observation. We're always chasing certainty, but we can never quite catch it.
And he believed that embracing that humility is precisely what separates true science from dogmatism. A scientist says, based on all the samples we've drawn from the ballot box so far, this law appears to hold. They should never say, this is the eternal, unbreakable truth of the universe. Because the universe is infinite, and our sample size is always, by definition, finite.
So we have this system built on imperfect induction, guided by probabilities, not certainties. And then he goes even further. Let's talk about imperfect measurement, segment 4. Jevons seems to think that even our best, most precise instruments are, in a way, lying to us.
Or maybe the better way to put it is that perfection itself is impossible in the physical world. He dives deep into the idea of continuous quantity. Things like space and time and weight are infinitely divisible.
You can always slice it thinner. There's always a smaller unit.
Right, you can cut a centimeter into millimeters, millimeters into microns, microns into nanometers, and so on forever. There's no smallest possible piece. And because of that, Jevons argues that no two physical things in the universe are ever exactly equal.
He brings up Shakespeare here, right? The merchant of Venice and Shylock demanding his pound of flesh.
It's such a brilliant example. Portia, in the play, tells Shylock he can have his pound of flesh, but on one condition. He must cut exactly 1 pound. No more, no less. Not even by the weight of a single hair.
And Jevons points out that, logically, Shylock is doomed from the start.
He's physically doomed. It is physically impossible to cut a piece of flesh or a piece of gold or lead or anything that weighs exactly 1.000000 with infinite zeros.
Yeah.
Pounds. There is always an error margin. You're always going to get 1.00001 or 0.999999. Exact equality is a pure abstract mathematical concept. It's not a physical reality.
So in the real world we inhabit, true equality is a myth.
Absolute equality is a mathematical abstraction, yes. In the physical world, all we ever deal with are approximations. He also talks about unstable equilibrium. He said, theoretically, you could balance an egg perfectly on the point of a needle. The mathematical equations say it's possible.
But practically speaking?
Practically, it's impossible. Because of what he calls infinite sensitivity. The tiniest breath of air, a vibration from a carriage passing a mile away, the thermal expansion of one side of the egg being slightly warmer than the other. Any of these infinitesimally small variables will knock it off balance.
Okay, so if everything is wobbly and inexact and impossible to measure perfectly, how on earth do we do science?
We manage the error, we accept it, and we work with it. This brings him to the law of error. It's why we take multiple measurements and then we average them. But Jevons has this really keen insight about what that average, the method of memes, actually is.
This average.
He says the average is a fiction.
A fiction? How so?
Well, think about it. If you measure the position of a star 10 times and you get 10 slightly different numbers because of atmospheric wobble and instrument error, you average them, you get a mean. But that final average number, it's very likely a number you didn't actually observe in any of your 10 measurements.
Yes,
it's a calculated number.
So it's a non-existent quantity.
It represents a non-existent quantity that is simply the most probable approximation of the truth. It's the point around which all your errors are most likely to cluster.
It's a ghost number that we all agree to treat as the real one.
That's a great way to put it. And he brings up the personal equation in astronomy, which was a real historical issue. It was discovered that two different astronomers watching the very same star across a wire in a telescope would record slightly different times. Why? Because their reaction speeds differed. One might just be consistently 0.2 seconds slower than the other.
So even the observer, the human being, is a source of error that has to be accounted for.
Exactly. The human machine is flawed and wobbly, just like everything else. So science, for Jevons, becomes the rigorous management of error and the calculation of probabilities, rather than the search for absolute, exact, certain truths. We end up measuring the measurer just as much as we measure the object.
This paints a picture of science that is incredibly powerful, but also kind of fragile. We're making educated guesses about the laws of nature, we're averaging out our own mistakes, and we're just hoping the infinite ballot box doesn't decide to throw us a curveball.
It is.
Which brings us to the biggest picture of all. Let's go to segment 5, theology and the universe.
Yeah, you have to remember, Jevons was writing in the wake of Darwin. It was a time when many people felt that science and materialism were completely killing religion. This idea of the reign of law felt like a prison. If every atom in the universe is just following predetermined mechanical laws, where is God? Where is free will? Am I really choosing to speak right now, or are the atoms in my brain just playing out a chemical reaction that was set in motion at the Big Bang?
And Jevons, surprisingly, pushes back against this deterministic gloom.
He does, very strongly. He argues that this phrase everyone uses, the uniformity of nature, is actually an ambiguous term. Just because things have been uniform so far, that's our ballot box again, doesn't mean they are necessarily uniform forever. He says the law does not mean necessity. It just means we haven't seen the exception yet.
Yeah. And he uses the Babbage machine analogy here again, but for a completely different and fascinating purpose. This was one of my favorite parts of the whole treatise.
Charles Babbage, the father of the computer, was a huge influence on Jevons. And Babbage came up with this thought experiment. He said you could program his analytical engine to print the natural numbers, 1, 2, 3, 4, and so on, and it could do this for 1,000,000 years without fail. To any observer, the law of that machine is simply n+1. It would look eternal, unbreakable.
Because there's a twist.
But the programmer, Babbage, could have designed the machine with a gear that was set to trip only after, say, 100 million calculations. And at that exact moment, the machine suddenly prints a geometric number, or a square number. Then, just as suddenly, it could go back to the old n+1 series.
To the observer on the outside, that sudden change would look like a miracle. It would look like the fundamental law of the machine was broken.
But Jevons and Babbage argue it wasn't a breach of law at all. It was a higher order of law coming into effect. And by analogy, a divine creator could have programmed the universe with miracles built into the very structure of its laws from the very beginning. So what looks to us like an apparent interruption of nature might actually just be a part of the program we haven't reached yet.
That is a staggering thought. It completely reconciles determinism with the possibility of the miraculous. The miracle isn't a violation of the universe's code. It's a hidden function that was in the code all along.
And this connects directly to his views on entropy. He discusses what was then called the dissipation of energy, which we now call the second law of thermodynamics, or the heat death of the universe.
The idea that everything is slowly, inevitably cooling down and running out of useful energy.
Right. And he says, well, if the universe is like a clock that's winding down, that logically implies it must have been wound up in the first place.
Yeah.
It implies a beginning. Jevons uses this as a scientific refutation of what he called materialistic eternity. He says the science of his day points directly to a finite duration for the current order of things. It had a start, and it will have an end.
And he closes this grand vision with a very poetic, almost mystical reflection. The infinite library.
The air is a vast library. It's just a beautiful concept. Jevons argues that every thought we have, every word we speak, every whisper moves particles of air. Those particles collide with other particles. The motion dissipates and becomes incredibly complex. But because of the conservation of energy, it's never technically lost.
It's all still there.
It's all still there. So theoretically, the entire history of every word ever spoken on Earth is eternally registered in the ongoing movement of the atoms of the universe.
Yeah.
If we had infinite computing power, if we were Laplace's demon, we could read the air around us right now and perfectly replay the speeches of Cicero or the secret whispers of a conspiracy from 500 years ago.
It's all just there, written in the wind. We just don't know how to read it.
Yet.
Well, that is a perfect segue to our outro segment. We've covered the substitution of similars, the logical piano, the infinite ballot box, and the fundamental imperfection of all our measurements. Now let's take Jevons' rigorous logic and push it right off a cliff. It is time for thought experiments.
And here comes the disclaimer. The following segment involves outlandish but plausible philosophical thought experiments inspired by the work we've discussed. These are for entertainment and educational purposes only.
Experiment number 1. I'm calling it the cosmic switch.
Okay, this one plays on that Babbage machine analogy in the infinite ballot box. We operate under the assumption that the fundamental laws of physics, gravity, thermodynamics, electromagnetism are constant and eternal. But Jevons would say that's just a high probability belief based on past experience, not a logical necessity.
So the scenario is this. Imagine the laws of physics are not eternal. They are merely a program, a cosmic computer code, set to run for exactly 13.8 billion years, which is roughly the current age of our universe.
Right, and imagine that tomorrow, at high noon, the program simply hits line 10,000. The gear trips, the switch flips. Suddenly, gravity becomes a repulsive force instead of an attractive one. Massive objects start pushing each other away. Entropy reverses. Your cup of coffee on the table starts getting hotter instead of colder.
The terrifying twist here is that Jevons would argue we have zero logical proof that this won't happen.
None whatsoever. We have an extremely high probability it won't happen, based on drawing a lot of white balls from the ballot box. But we have no logical necessity. We are living on a knife edge of probability, and we mistake constant repetition for a guarantee. The cosmic switch could flip tomorrow, and it wouldn't even be a violation of the true law of the universe, just the end of the temporary law that we happen to be living under.
It puts our confidence in the uniformity of nature in a very scary new light.
It's like we're the turkey being fed generously by the farmer every single day, concluding that the law of the universe is farmers are benevolent, right up until the morning of Thanksgiving.
Chilling. Okay, experiment number 2, the universal recorder.
This one takes that air is a library concept and injects some modern technology. Jevons said the air mechanically records every sound, every event.
So, the scenario. We build a quantum computer of unimaginable power. Let's call it the Jevons machine. It is capable of mapping the precise position and vector of every single molecule in a sealed room.
Now, if we have a perfect snapshot of the position and momentum of every molecule now, and we know the laws of mechanics, we can perform inverse deduction. We can run the entire simulation backward in time. We can reverse the vectors.
So we could reconstruct the sound waves that disturbed those molecules 10 minutes ago, or 10 years ago.
Or theoretically, 500 years ago, assuming the room was perfectly sealed, or we had enough computing power to map the entire outside world as well.
The implication then is that privacy is just an illusion created by our limited computing power.
Precisely. If Jevons is right, and mechanical effects are never truly lost, then the past is not gone. It's not even past. It is physically locked into the present arrangement of matter all around us. History isn't just a memory. It's a massive unread data set. If you committed a crime alone in a locked room 10 years ago, the air in that room is still, in a sense, vibrating with the evidence. We just don't have the eyes to see it yet.
That is both terrifying and exhilarating. It suggests that nothing is ever truly forgotten. The universe remembers everything, literally.
Jevons teaches us that the world is rigorous, it's mathematical, and yet at the same time, it is completely saturated with the unknown. We're walking through a library filled with secrets we can't read, making educated guesses about a future we can't truly predict.
We're all just drawing balls from the infinite ballot box and hoping for the best.
And hoping the next one is white.
This has been Talk Treatises, a deep dive into the incredible mind of William Stanley Jevons.
Keep calculating.
And mind the error.